Well, you might have thought you'd seen the last of him for this subject, but haha, he's back, Leonhard Euler, looking as disappointed in you as ever. And here he comes with a definition in graph theory of an Euler path. An Euler path is, well, as the name suggests, a path in a graph, but it's one that uses every edge exactly once. We could also have, in the same way, a path that starts and ends at the same node is also a circuit, and an Euler circuit is just an Euler path, which is also a circuit. Now, in justifying whether or not a graph contains an Euler path or an Euler circuit, well, if any node has odd degree, then it definitely is not possible to use every edge of the graph without getting stuck somewhere. So if every node has non-zero even degree, so if it has 0 degree, it's disconnected. So if every node has non-zero even degree, then there will be an Euler circuit in the graph. So that doesn't rule out it containing an Euler path if there's either 0 nodes of odd degree or exactly 2 nodes of odd degree, and those could be at the start and end of this path. There's a famous historical problem in mathematics, and it was actually proven, or the solution was found by Euler himself. And this is known as the Königsberg bridge problem. And it's named after the city of Königsberg, which was then in Prussia. Prussia later being in Germany, and also now it's in Russia, called Kaliningrad. So the problem is still called the Königsberg bridge problem, as it was formulated and solved by Euler in the 1700s, rather than the Kaliningrad bridge problem. And in the city of Königsberg then, there were 7 bridges spanning the river network. No idea how many there are now, but this was the visualization of the bridges as they were. So this odd sort of like island type thing had divided the city into 4 regions. So there's a bit sort of above the rivers, a bit below the rivers. There's the island bit in the middle, and then there's the bit to the right of the rivers. And these 7 bridges spanned the network. So the question was whether it would be possible to plot a path such that a traveller could walk over all 7 bridges without crossing any one of them more than once. So this is basically a question saying, can we find an Euler path on the graph that is equivalent to that map? So what graph is equivalent to that? Well, there's 4 regions of the city as split by the river, and 7 bridges, so 7 connections or edges between those 4 regions. So if I just mark the 4 regions with a node each, then the bridges are the edges. So that still doesn't look that much like a graph in the sense of how we've previously seen them, but it's equivalent to this. So the 4 nodes are the 4 regions, and we can see that some of them have more than one edge connecting them. Like there are 2 bridges going from the bit between the branches of the river to the part above, and 2 going to the part below. So the node in the center on the left is joined by edges 1 and 2 to the same node, and similarly going down, it's joined by edges 5 and 6 to the bottom node. As we said, it was Euler himself who proved that there was no possible path around all 7 bridges without reusing a bridge at least twice. Well, the Irish are not to be outdone by one overachieving Swiss man, and there is a similar definition to Euler paths and circuits. In the same way as an Euler path or circuit had to use every edge exactly once, we can also have a similar thing, but looking at using each node or going through each node exactly once. And the similar idea, but looking at nodes rather than edges, is a Hamiltonian path. And in the same way that we had Euler paths that were circuits being Euler circuits, we also have Hamiltonian circuits. So it goes through every node exactly once and will wind up terminating back the same node which started. So we won't go into it in this subject. I'm just going to mention this as a bit of an aside, that we've got similar properties in the same way as we had some properties that a Euler path or Euler circuit had to satisfy. There are certain properties that Hamiltonian paths and circuits have to satisfy. But credit where credit's due, and this is William Rowan Hamilton.